Hello everyone, welcome to another episode of Cooking with Calculus!
I'm Spicin It Up Sanil.
I'm Juicy John.
I'm Chris and I cook it up.
And I'm Whole Lotta Enchilada Ethan.
For this episode, we will be working with our extra large chewy cookie.
With calculus.
We will begin focusing on the rate of change of the volume as it expands after baking. Let us begin.
First, we have to measure the radius with Sanil's handy dandy rulers.
From this, we can clearly see that the cookie is 10 inches in diameter and 3/8 inch in height. When dividing the diameter by 2, we get a radius of 5 inches.
We can also quickly figure out the volume of our cookie by using the equation pi r squared times height.
Next, we have to put the cookie in the oven for 10 minutes at 350 degrees Fahrenheit. Now, all we have to do is wait.
So what should we do now?
Let's watch some TV.
Okay, fine.
Are you looking to ride the wildest, craziest, awesomest coaster in your life? Then check out the soon-to-be-built Fiery Fist of Pain, hopefully coming to a Six Flags near you. This ride will get your brain twisted like a dollar churro from Costco. Whoa, this looks so cool! Our coaster travels at an eye-popping top speed of 55 miles per hour. If you'd like to make our ride a reality, visit coastercrusher.net to fund our campaign. Wow, that's so fast! It's so rad! That's like a car driving on the highway! How's that even possible?
Classic Sanil.
Let's start from the very beginning. If you remember, we got this old guy named Julius Myers who's very smart about physics.
Yeah, he created a few very important rules that you should definitely know, Spicin It Up Sanil.
Oh, okay, very interesting. What law are you talking about?
Well, it's all about the law of conservation of energy, you see. The smart man Julius Myers says that energy will neither be created nor destroyed. Rather, the initial energy will be equal to the final energy.
Yeah, let's think about this from a 2D perspective.
When looking at the Fiery Fist of Pain, it is a hot by distance graph, which can also be seen as a potential energy by distance graph.
Ah, okay. So that relates to that guy's law of conservation of energy, right?
Yes sir, the total energy is conserved throughout this entire ride.
So how do you find the energy?
Well, that's easy! All you do is you know that the total energy is equal to the potential energy at the max height because the height is maxed out and the kinetic energy is essentially 0 because your velocity is 0.
What are potential and kinetic energies?
Oh my goodness!
Sanil and hot and godly!
Godly!
Well, potential energy is essentially mass times gravity times height, or in short words, PE equals mgh. Kinetic energy is the energy stored in the movement of the object. In this case, it's the roller coaster. Kinetic energy equals 1/2 times mass times velocity squared. We can use this to find the speed of the coaster at any point with a little bit of clever algebra.
Because we know that the initial energy is equal to the energy at any point, we can set them equal to each other with this equation here. Now, just do a little bit of algebra, cancel out the masses, we can see that velocity squared is equal to 2 times gravity times the change in height.
Oh, I see. And you can just find the change in height by subtracting f of x from the max height. Then you just take the square root and there you have it. V equals square root 2g times h minus f of x.
And that is your velocity equation.
Okay, it's all coming back to me like one big brain blast.
So do you get how to calculate, say, the max velocity?
Psh, of course. Wait, never mind. How do we do that?
How are you even in calculus?
Well, my mom tells me to do my homework every day, and if I don't, she won't let me watch Saturday cartoons.
Okay, eraser first. Marker me. Take that. And here we have it. Starting off with the velocity equation, square root of 2g times the change in height. From there, you just do a little plug and chug and there you have it.
Pretty easy, because you know that g is 32.2 feet per second squared. Then we know that the max height is 75 feet, and the minimum is 27.1. So So all you have to do is find the difference of these two numbers, and you get 102.1. Multiply it all out, and you go with 81.09 feet per second, or 55.29 miles per hour.
No way! That's so crazy. Is that even possible? My mind is blown again and again. I love calculus. The applications, endless.
Oh yeah, you bet! The applications are endless. You can even find the time between any 2 points on the curve. Here, let me show you. Well, Sanil, it's really quite simple to find the time.
It is?
It is.
That's very complex.
Nah. Because we know that it's a height versus width graph, and we know, because of this, that the velocity is equal to the change in distance divided by time. With some simple algebra, we can rearrange this and we get time is equal to the change in distance divided by the velocity.
Interesting. How do we get time from that?
So, to put it in terms of time, we know that time is equal to the change in distance divided by the velocity. Now, but what is the change in distance? If you think about it, the change in distance is the total distance that the roller coaster has traveled along the curve. You can think of it as being a string, and if you were to cut it here, and if you stretched out that string so it were a flat line, that would be the total distance that the roller coaster traveled. So that is your ds, and you can find that with this equation right here. So ds is equal to the integral of the square root of 1 plus f prime of x squared. And you know the velocity, we found that earlier, is equal to the square root of 2 times gravity times delta h, or the change in height. So we put the ds, this equation, over the velocity, this equation. And in the end, you get this as a whole equals time. Do you understand?
No.
One day you'll get it with your pea-sized brain, Sanil.
Wow, cool. I wonder if you could find the equations for acceleration.
Well, we could probably find that if it were a position versus time graph.
What? Then how would you even solve for velocity?
Well, to do that, all you would do is take the derivative of the position versus time graph. That would give you velocity versus time.
What about acceleration?
Oh, well then to do that, you just take the derivative of velocity, and that gives you acceleration.
Ah, okay, I see. What happens if you take the derivative of acceleration?
Well, that would be jerk.
What's that, Ethan?
No, you idiot. That's the physics application. The change in acceleration due to time. You see, but if your jerk is too large, you'll experience large amounts of g-force and you'd probably die. Die? Yes! Die!
Wow, that was so exhausting. I think I needed a break because I've had too many brain blasts. Oh!
Typical Sanil.
True. My brain.
So what do we do now?
How about some more calculus?
Are you serious?
No.
Okay, whatever, let's go.
Fine. Optimization.
Oh, rate of change.
Oh! You're so smart! Wow. Wait,
Wait, did you hear that? I think it's time to check the cookie.
Yeah!
Oh my god!
Whoa! This is one crackin' crispy calculus cookie.
Most importantly, check out how much it expanded.
With a new radius of 5.5 inches and a height of 11/16, we can now calculate the rate of change of the volume.
To start off, we have to find the derivative of the volume, which is just right here. The initial height was 6/16, and the final height was 11/16. This gives us a rate of change of 0.021 inches per minute.
With the initial radius of 5 and the final radius of 5.5 inches, this gives us the rate of change of the radius, which equals 0.033 inches per minute.
Then we can just plug in some numbers and see that the cookie volume expands at a rate of 1.43 inches cubed per minute at 15 minutes.
Thanks for watching this episode of
Cooking
with calculus. The total energy.
Dang it! Oh my god.
Well,
Okay, I'm keeping it going.
Well,
I'm keeping it.
here's my number, so call me maybe. Hey, I just met you, and this is crazy. But here's my number, so call me maybe.
Large amounts of G-force and would probably. What? And would probably die. What? What? Why would you write that?
let's go.
Ah!